Greetings to the panel of examiners and my supervisor, Associate Professor Dr. Jacey Lynn Minoi. My name is Muhammad Afifuddin bin Salehudin, 83635, and today I will be presenting my final year project named RapidGO and Offline First Deterministic Navigation Engine for GPS-Denied Transit Environments. This project addresses a critical, often overlooked failure in modern navigation, the last mile, information gap within the Klang Valley Integrated Transit Network. Specifically, we are engineering a solution that works where Google Maps does not, underground. Background: the fragmented network. To understand the urgency of this solution, we must first look at the context. The Klang Valley Transit Network serves millions of daily commuters, yet it suffers from severe systemic fragmentation. As you can see, the ecosystem is split between multiple operators, Prasarana, KTM, and ERL, each operating in silos. Currently, a commuter often requires 3 different apps just to plan a single trip, one for the schedule, one for the map, and another for the fare. This disconnected information architecture creates a high cognitive load for users, but the problem goes deeper than just inconvenience. Problem statement. The core technical problem that I am solving is the GPS-denied reality. For the problem number 1, first, we have an infrastructure failure. Approximately 40% of the new MRT Putrajaya line operates underground. In these subterranean tunnels, GPS signals from satellites are physically blocked. Number 2, this leads to the blind commuter phenomenon. When a user enters a tunnel, the navigation app loses its location lock. It cannot be rerouted, it cannot identify which exit to take, and it cannot estimate arrival times accurately. And the final problem is, this happens because of architectural dependence. Current market leaders like Google Maps rely on always online architecture. They depend on live APIs and constant GPS telemetry. My thesis is simple: no data should not mean no navigation. Literature review. I have conducted a comparative analysis of existing solutions to validate this gap. Referring to the table, Google Maps offers excellent intermodal routing but fails completely underground and relies heavily on online connectivity. Moveit is a strong competitor, but it is crowdsourced and ad-heavy, requiring a constant data stream to function. RapidGO proposes a paradigm shift. It is offline first. It is designed specifically to work in underground tunnels using a deterministic logic rather than live sensors. Furthermore, unlike standard apps that optimize only for distance, RapidGO employs a multi-criteria approach, factoring in cost, time, and historical density. Project aim and objectives. The primary aim of this project is to engineer a deterministic navigation companion that functions independently of live telemetry. To achieve this, I have defined 3 specific engineering objectives. Objective number 1, to develop a multi-criteria route selection or MCRS engine. This algorithm allows users to optimize their journey based on their priorities, whether that is saving money, saving time, or avoiding crowds. Objective number 2, to implement a manual displacement engine or MDE. This is the core mechanism that replaces GPS in signal-denied zones. And finally, to construct a local deterministic database. This involves digitizing the internal topology of stations to enable micronavigation without internet access. Project scope. To ensure feasibility within the final year timeframe, the scope is strictly defined. In scope, the system focuses on the MRT Putrajaya line as the primary testbed due to its complex underground architecture. This project will be built including the offline pathfinding engine, the manual scroll interface, and integrating the 2026 fare tables. Out of scope, this project will explicitly excluding real-time GPS tracking via API, as that contradicts the offline premise. This project will also exclude physical payment gateway integrations. The system calculates fares but does not process banking transactions. Methodology. For the development methodology, I have selected evolutionary prototyping. This model is essential because we are dealing with a novel navigation logic, the offline state machine. We cannot simply waterfall the design. We need to build the core logic, test it against complex station layouts, and refine it iteratively. This cycle of analysis, design, prototype, and validation ensures that the manual displacement engine feels natural to the user before the final deployment. Requirement elicitation. A critical component of this research is the data source. Since I cannot rely on Google's APIs, I had to build my own ground truth. I utilized a data triangulation strategy. For the document analysis, I obtained and analyzed the MRT Corp retail space guidelines. These are technical blueprints that explicitly demarcate paid versus unpaid concourse zones. Second, site audits. I perform physical verification of the choke points, specifically the escalators and logic gates, to calibrate the walking time constant. Community validation. I cross-reference with these open source rail databases. This allowed me to construct validated digital twins of the stations like Damansara Damai, ensuring the system's internal map is topologically accurate. Significance of the project. The significance of RapidGO is twofold. The first one is socially. It empowers commuters. It removes the anxiety of getting lost in complex interchange like TRX when the signal dies. And second one, for technicality. This project contributes to the field of software engineering by proving that offline-first architecture is a viable, robust alternative for modern transit applications. We are proving that you don't need a server to navigate a city. Proposed solution. The RapidGO concept. We are moving to the proposed solution. The core concept of RapidGO is the travel companion. In traditional apps, the satellite is the source of truth. In RapidGO, the user replaces the satellite. We are shifting the paradigm from sensor-based displacement, which is fragile, to user-based displacement, which is robust and deterministic. System architecture. The hybrid model. To support this, I designed a hybrid data architecture. Referring to this ERD diagram, unlike a standard SQL database, we split the data into two layers for offline performance. First is the SQLite layer. This handles the highly structured relational data such as pair matrices and schedule logic. It allows for complex queries like find the cheapest route. The second layer is the JSON layer. This handles the topological data. We store the station nodes, edges, and escalator connections as lightweight graphs. This ensures the app remains fast and responsive even on lower-end devices without network access. Technical dive. The MCRS engine is the brain of the system, is the multi-criteria route selection engine. Referring to this flowchart, standard navigation apps use Jigsaw's algorithm to find the shortest distance. MCRS uses a modified A-star algorithm that runs three parallel heuristic vectors. First is the cost vector, is to minimize the Malaysian ringgit spent. Second one is time, to minimize duration based on assumed travel speeds. And the last vector is density vector, utilizing historical crowd data to avoid peak congestion. And referring to this formula, these vectors are weighted and summed in the utility score formula you see here, allowing the system to recommend the best route mathematically, not just the closest one. The second part of the technical deep dive, Manual Displacement Engine MDE. The most distinct innovation of this project is the Manual Displacement Engine MDE. Referring to this mockup, this is the feature that solves the blind commuter problem. When the app detects it is offline or underground, it decouples from the system clock. It introduces a human-in-the-loop mechanism. The user interacts with the scroll wheel interface to scrub through their journey progress. The logic: as the user scrubs, the app updates their position on the map. The safety net: the system uses logic gates. It won't let you scrub past a station until you have verified you have arrived. This ensures the digital state remains synchronized with the physical reality, even if the train is delayed. Micro-navigation, station topology. Furthermore, we address the vertical navigation gap. Most maps treat a station as a single dot. RapidGO maps the z-axis. We have digitized the node logic for the concourse, V1 and V2. By deriving this data from the elicited retail guidelines, the app can guide a user specifically from the platform to the correct escalator, bridging the micro-navigation gap inside the station. Interaction design. Finally, for the interaction design, we introduced the Red Anchor manual geospatial query. Online app drains battery by constantly searching for GPS. RapidGO reverses this. The user drags the map to place the red anchor on their destination. This effectively tells the offline database, "I want to go here," triggering the pathfinding algorithm without a single byte of network data or GPS battery usage. Preliminary results or prototype progress. In terms of current progress, we are on schedule. The database schema is fully designed and implemented in SQLite. The station topology elicitation is complete for our pilot sample, which is the Putrajaya line. The last one, the high fidelity UI/UX design is complete as seen here in these screenshots, featuring the dark mode optimized interface for underground visibility. Project roadmap for FYP2. Looking ahead for FYP2, the roadmap is very clear. Phase 1, I will proceed with the code implementation using Flutter and React Native or React Native. Phase 2, I will integrate the MCRS mathematical logic into the application. Phase 3, the critical phase will be user acceptance testing. I plan to take the prototype into the actual MRT Putrajaya line tunnels to validate the manual displacement engine with real commuters. Conclusion. To conclude, RapidGO is more than just a trip planner. It is a resiliency tool. By bridging the information gap where Google Map fails, we are creating a resilient, offline and intelligent companion for the modern commuter. We are ensuring that even in the deepest tunnel, the user is never truly lost. Thank you for your time. I welcome any questions you may have. Thank you very much.